Howdy. Since several hours I tried to make a video about this very interesting article, which popped up today in my newsfeed, Life Science. Rare, rule-breaking quasicrystal found in chunk of fossilized lightning, published 1 day ago. A type of crystal that breaks the rules of ordinary crystallography has been found in a tube of melted sand from Nebraska. Fused sand from lighting or a downed power line, known as Flugurite. This Flugurite found in Nebraska holds a rare material known as quasicrystal. A tube of fossilized lightning from Nebraska's sandhills holds a rare type of quasicrystal that had previously only been found in meteorites and at atomic bomb test sites. Quasicrystals are materials that break the traditional rules of crystallography. Before they were first reported in 1984, scientists thought materials could either be crystalline with symmetrical repeating patterns or amorphous, meaning randomly arranged and disordered. In addition, scientists believed crystals could only be symmetrical a limited number of times when rotated around on axis. 2, 3, 4, or 6 times. Quasicrystals break those rules. They are put together in an ordered pattern, but that pattern does repeat. They have also rotational symmetries that no ordinary crystal can achieve. Let's read that again. They also have rotational symmetries that no ordinary crystal can achieve. A quasicrystal with icosahedral symmetry, for example, can display 5-fold symmetry around 6 different lines of rotation. What's that commercial? Is this kind of AI commercial just made for me to prevent 100% targeted attacks on power plants? What the fuck? Yeah. Waterfall security. Very interesting. Anyway, quasicrystals were first discovered in the laboratory. In 2012, however, Paul Steinhardt, a theoretical physicist at Princeton University, and Luca Bindi, a geoscientist at the University of Florence, Italy, announced the discovery of a natural quasicrystal in a meteorite that fell on the Kamchatka Peninsula in northeastern Russia. The researchers then created more quasicrystals in the lab by mimicking the high temperatures and high pressures that might be found when rocky bodies collide. They then turned to another place where a very rapid transition to high temperature and high pressure occurred. The Trinity atomic bomb test site in New Mexico. There, they found more quasicrystals in minerals from beneath where the atomic bomb exploded. For this reason, I started to think of other materials formed in similar conditions. And I thought of Flugurites, materials formed by lightning strikes, Bindi told Life Science in an email. Dramatic discharge. Flugurites form when lightning hits sand, fusing together the grains in a gnarly branching tube of glass. Bindi collected multiple Flugurites in his search for quasicrystals. The one that held this rare form of matter came from the sandhills of Nebraska, near the village of Hyannis. This area of Nebraska is made up of grass-covered sand dunes. The Flugurite was found near a power line that went down in a storm in 2008. In total, it was about 6.6 feet, 2 meters long, and up to 3.1 inches, 8 centimeters in diameter. That's a huge Flugurite. No one witnessed the event, so the researchers aren't sure whether lightning struck the power line and created the Flugurite, or whether the line went down in the wind and created the Flugurite with its own electrical discharge. So they don't know if the lightning strike hit straight to the ground or did the electricity come from the power line. The end result is exactly the same. And they went to some nuclear test site to find these Flugurites and these other things, crystals. Either way, the resulting branched glass contained a mixture of materials from the sand and the metals in the electrical line, including manganese, silicon, chromium, aluminium, and nickel. To melt these materials, the temperature of the sand must have briefly reached at least 3,110 degrees Fahrenheit, 1,710 degrees Celsius. The researchers reported on December 27th in the journal Proceedings of the National Academy of Sciences. Hunting for quasicrystals. Using a scanning electron microscope, Bindi, Steinert and their colleagues found a 12-sided, 12-angled crystal with 12-fold symmetry embedded in the Flugurite. Quasicrystals with this sort of symmetry are even rarer than quasicrystals in general, the researchers wrote in their paper. Quasicrystals with 10-fold symmetry or icosahedral symmetry are more common. Oh. The discovery points to new places to look for natural quasicrystals, Bindi said. It demonstrates that transient extreme pressure temperature conditions are suitable for the synthesis of quasicrystals, he said. In other words, very high voltage. Other potential places to find quasicrystals, he said, might be in impact glasses formed when large meteorites or asteroids hit Earth, or in parts of the moon's surface that have been hit by asteroids. Editor's note, update, and blah, blah, blah. So, how is that possible? After finding these things, like where lightning struck and stuff, they still search for impact craters.